Hello and welcome to my CFD Cyclone tutorial. In this tutorial I'm going to show you how to simulate a cyclone separator using ANSYS ICEM CFD and ANSYS FLUENT. This video is in addition to my master thesis, which focused on the design of a new compact cyclone separator for microscale fluidized bed combustion. Here you can see the geometry of the cyclone I've chosen for this tutorial, test conditions during the experiment, as well as the two key performance indicators for cyclones, the fractional separation efficiency and the total pressure drop. This tutorial consists mainly of two parts. First, the creation of the hexahedral mesh in ICEM, and second, the numerical simulation in FLUENT. As a first step, we are going to create the topology we want to investigate as a 3D CAD model. As you can see, I've already prepared a sketch of the cyclone. So we only need to do a rotation of the sketch, 360 degrees, and then create the tangential inlet. So, as you can see, I used the CAD system Solid Edge, but any other common CAD system will do. Just make sure to save your model as an IGS file, so that way there will be no problems when importing models into ICEM. So now to the first part of the tutorial, the design of the hexahedral cyclone mesh. In ICEM CFD, click File, Import Model, and choose the CAD model we've just created. So pull down to IGS file, and here's our tutorial cyclone model. Now you can leave these default settings and simply hit OK. So here's our geometry. Let me turn on the surfaces, solid display them. And I should point out that you could have also created this geometry in ICEM instead of an actual CAD program. But since I'm so used to CAD modeling, I prefer this way of importing models into ICEM. Now the first thing to do will be to add and modify some of the points and circles of the current cyclone geometry. So we'll go to the Geometry tab, Points, and first create a single point on every quadrant of this circle. And we also need a midpoint. And then copy this point at the end of the vortex finder up to the upper plane. So we'll have a distance of 0.81 meters in Z direction. Choose the point, middle mouse button, and now we can create a simple circle. And a fast way to create a single point on every quadrant is to use the Project Point to Curve tool. So first choose the curve and then the three corresponding points. Done. And we'll need 4 more points in the inner circle for our innermost O-grid block. But you'll see what these are for later. Now, furthermore, you should always work with complete circles. So let's delete this one, delete curve, and use the midpoint to create a new one and replace it. And again, we're going to project points to every quadrant. Okay. Now, to keep things as minimal as possible, I'm going to assign some of those curves and points to individual parts. So I right click part, create part, and I'm going to name this tangential inlet. You can choose any name you want, doesn't really matter here. And I only want to select curves. And now only want to select points. Okay, then click the middle mouse button and we get our tangential inlet part. Second part I'm going to create is the upper plane. Again, I click create part and I'm going to name this plane 2. You're gonna see why in a few minutes. I want to select points and curves, draw a box around that upper part. Middle mouse button and we get plane 2. I'm going to give this another color so we can better distinguish them. Now if we go to top view, we can see that there are altogether 7 planes over the full height of the cyclone. Plane 1 at the outlet of the cyclone, plane 2, plane 3 at the bottom of the inlet, plane 4 at the end of the vortex finder, plane 5 at the beginning of the cone, plane 6 at the end of the cone, and plane 7. Now instead of creating all these curves and points for all the planes individually, I'm simply going to copy plane 2 in Z direction. So I'm only viewing plane 2 and go to transform geometry, check copy, select all of plane 2, and I'm going to offset this in Z direction. So for plane 1 it's 0.12, and if you don't know these distances of each plane to plane 2, you can use the measure tool, or you can look them up in your CAD model works as well. So plane 3 is minus 0.175, plane 4, 5, 6, and 7. Now if we go to top view again, you can easily check if all these new planes are aligned to the original part 1 curves and points, which means that I obviously typed in all the right offset values. Now all these new curves and points are still assigned to plane 2. So we need to create a part for each plane. So go back to top view and I'm going to create another part and name this obviously plane 1. Plane 3. Plane 4. Okay, done. So now we can view each plane individually. Now if we view the surfaces, and I have to turn on part 1, we can see that plane 6 and 7 are below the cone, and they obviously have to be scaled to the right size. So I only view plane 6 first, and I'm going to use the scale tool. I don't want to copy, I want to keep the original files to be scaled, and I'm going to select all of plane 6, and I want to scale in X and Y direction. So I need an X and Y factor. And I've already prepared the calculation of the scale factor between plane 5 and plane 6 in the draft, as you can see here. So back in ICEM I type in 0.45 and same for the Y factor. Okay. Now if we turn on the surfaces, you can see that the curves and points have been scaled to the right size. Now normally I just delete the outer circle and leave the original one, and I add this to part 6. So I want to select only curves. And the same thing goes for plane 7. So again, transform geometry, select all of plane 7, and X and Y factor are correct, and we have the same result for plane 7. Okay, now we are done with the geometry part. This might be a good time to save the current project. And if you're wondering what all these planes and curves are for, you're going to see that in the following blocking part. Now the initial step here is to create one big block of the whole geometry. So leave all these default settings and just hit OK. And I'm going to show you my plane and layer blocking technique. So the first thing I'm going to do is to view only plane 1 and the edges and vertices from the block, and associate those vertices to the corresponding points. And align the vertices so everything snaps into place. Now if we go to the front view, you can see that the Cyclone has 4 layers of blocks or edges. 1, 2, 3, 4. And this means that we are going to need 3 O-grid splits of the initial block. So first split, and we're going to select faces where the O-grid passes through the wall. So apply for the first O-grid split. Second one, and another one. Actually go to the front view, so it's easier to do an O-grid split. And select the faces. Okay, now that the O-grid split is done, I'm going to do another split, but this time in Z direction, and I'm going to split all the blocks in every plane. So display all the planes, go to view, left, choose split method, prescribe point, visible, and you can select any edge at any point in the plane. And it's going to do a split of all the 3 O-grids. And if I view the blocks, you can actually see that. And let's check with index control. Yes. 8 planes of edges. Okay, so my approach to associating such geometry is to treat each plane separately. So I'm only going to view plane 1 and use the index control to view only edges in plane 1. And I'm going to associate those edges to their corresponding curve. And I show the associations. Done. So we proceed with plane 2. So view only curves of plane 2 and all the edges of plane 2. And there's actually a much faster way to associate these edges. And again I use index control to view only one layer at a time. So I could click on these classes or simply hit the key V for visible, which selects all the visible edges on the screen, and then click on the corresponding curve. And you can see this is a much faster technique. Then plane 3, same thing. And plane 3 and 4 are actually really close to each other. And here the plane layer technique comes in really handy. Otherwise this would be really hard to distinguish which of the curves or edges you have selected. And so I can use index control and only view plane 4. And I can make sure that I select all the right edges or curves. So let me view plane 3 and 4. And you can see this would be really hard to select the right edges and curves each time. And next is plane 5, which is, I think, the beginning of the cone, so we're still in the large diameter area. Right. Now plane 6. Here we actually have to associate the vertices to their corresponding points, because we are now at the end of the cone. So we need to go to associate, vertex to points, and I'm actually going to switch to the top view, oh no, the front view, to associate these vertices. Then I'm gonna use index control to view only one plane again and associate to the curve, just as we did before. Okay. You have to be careful because there are actually two curves from the original part 1. And if we go to plane 7, you can see that these are still in the original position. So we're going to use again align vertices, and this makes them snap into the right position. So we don't have to use the associate vortex to point in plane 7. And here the thing again. Using index control to view only one layer and associate them to the corresponding curve. Okay, now click reset, and you can see that all the edges are associated to the corresponding curve. Got display show associations and view all the geometry. Now if I view the blocks and display the surfaces, you can see that there are still some blocks between layer 1 and 2 which are not part of our topology, which means we can delete them. And I'm going again to use index control to view only the blocks between plane 1 and 2 and make those inner blocks disappear. And these are the blocks which are not part of our topology, so I click delete block, draw a box around them and delete them. So the only block missing is the inlet between plane 2 and 3. So let me display only plane 2 and 3 and then use index control. And of course we need the curves and points of the tangential inlet. And I'm going to do a split of this block into 2 blocks. And this time I'm going to block select selected, because we only need to split this block here. Pre-square point, that's correct. And I'm going to split this block on this edge with this point. And now I only need to associate these new vertices to the corresponding points. Okay. Now we have actually one face on this block. Let me turn the faces. And we can do an extrusion of this block. So we go to blocking, extrude, and I usually use the interactive mode, which will probably give me an error right now. Yes, of course. Because there are new dimensions in the index control. Oh, I can reset this. And I'm going to associate the new vertices to their corresponding points. Done. So now we do have all the blocks we need. One thing still missing is the vortex finder, which is not part of our topology, obviously. So we need to assign this to a new part. And I'm going to use index control to view only the blocks of the vortex finder. And what I usually do is go to blocks, right-click blocks, and blank these blocks from the vortex finder. And if I reset my blocks, I can see that the blocks from the vortex finder disappeared. And if you look to the part branch, you can see that the actual blocks are assigned to a part called solid, which is obviously wrong, because these are not solid blocks but fluid ones. So I'm going to create a new part called fluid, but I'm not going to add any curves or points in this case. I'm going to add blocks. In this case, all blocks visible on the screen, so I could select them with the classes. And now, if I display the blanking, I can see there are two kinds of blocks. One called solid, which is the vortex finder, and one fluid, which is the actual cyclone we want to investigate. Now that we are done with the blocking part, we can proceed with the mesh. So go to the mesh tab, surface mesh setup. I'm going to view all of the surfaces, select all of them, and give this a maximum size of, say, 0.017. Apply. OK. Go back to the blocking tab and update all of this. And now we should be able to preview some pre-mesh. Click yes, and you can see that we already got a quite decent cyclone mesh, which I'm going to improve in some areas. But first let me show you the solid blocks, which are our vortex finder. And we don't need to worry about this, we can disable it. We only need to deal with the fluid blocks. So let me start in this area. Go to the mesh parameters, select one of the edges, and give this like, let's say, 25 nodes. Make sure you copy to all parallel edges, apply, disable pre-mesh, and enable it, but recalculate it. And you can see that we got a much better mesh now in this area. Another thing you want to do is to add some prism layers at the walls in the cyclone. Well, not only in the cyclone, actually every geometry you want to investigate should have some prism layers at the walls. So I add one of the edges here and give this like 22 nodes and spacing 1 of, say, 0.03. I usually go with a grow rate here of 1.1 or 1.2. And we also need to do some spacing in the spacing 2 area and give this again a smaller size. 0.00, let's go with 3 and 1.1 again. Apply. OK. And let's recalculate our pre-mesh. You can see we got some prism layers at the wall, let's say like 3 prism layers. And we want to do the same thing for the vortex finder. So let's select one of the edges in the vortex finder. 4 nodes, well, we want to give this at least 11 and a spacing of 0.025 and ratio 1.1 again. Apply, and let's see what it looks like. Well, seems to be alright. Another prism layer I want to add is at the end of the vortex finder. And for this I'm going to disable pre-mesh, view only edges, and select one of the edges and give this 26 nodes. And we have to go to spacing 2. Well, the black arrow here indicates spacing 1, so the opposite side is spacing 2. And I'm gonna give this a spacing of, say, 0.003 again, and also grow ratio of 1.1. Apply. OK. Recalculate pre-mesh. You can see that we got another prism layers at the end of the vortex finder. And a really useful tool to check your pre-mesh is to use some cut plane. So right click pre-mesh and go to cut plane, and you gotta disable the pre-mesh now. And let me view some of the curves so you see where we are on the cyclone. And you can go over the full height of the cyclone and see what your mesh looks like on the inside, so to speak. And you can see these prism layers we created. Well, let's go to the vortex finder height. So small prism layers all around the vortex finder. And we could also check one of the, let's say, the Y plane. Let's zoom in here. And you can see again the prism layers all around the pipe of the vortex finder. And this high resolution mesh in the area of the vortex finder is actually really important, because the total pressure drop over a cyclone is normally subdivided in 3 contributions. So we got losses in the entry, losses in the separation space, and losses in the vortex finder. And while the first ones are often negligible, the losses in the vortex finder are by far the largest. So we really want to have a high resolution mesh in this area. And if you want to check your quality of your mesh in general, you can use one of these quality criterions. They actually look quite a lot criterions, but I usually go with determined 2.2.2. I only want to see where my bad elements are. And you can see, yes, we got some really bad elements in the cyclone. And let's disable pre-mesh to see where they are, and yeah, they're usually in the inlet part of the cyclone. That's just a thing with these cyclones. There isn't really a way around this. If you display the pre-mesh, you can see that there will obviously be some really, really bad elements in this part. But that's just the way it's gonna be. So we're done. And one thing we need to do is to add some boundaries to our mesh. So I view only the surfaces, and we're going to create some parts. Create part, and first thing will be a pressure outlet. I'm going to select the end of the vortex finder. And the thing is, if you call this surface pressure outlet, Fluent will automatically assign the surface to a pressure outlet boundary condition, which really saves a lot of time in Fluent later. And I'm going to create another one called velocity inlet. And the third one called wall dustbin. Okay. Now we're done with the mesh. Let me show you the final mesh. See what it looks like. And the last thing we want to do is to export this mesh to a mesh file. So right click pre-mesh, convert to unstructured mesh. And we get a new branch called mesh, which is the actual mesh we're going to use in Fluent later. And we still need to export this mesh to a mesh file. So go to output, save comport, yes, always click yes here. And you can leave these default settings. And let's call this mesh Cyclone tutorial mesh. Done. It's going to take a few moments. more or less. But eventually we're done with the translation. So we are now finished with the meshing part and proceed in Fluent. So now to the second part of the tutorial, the numerical simulation of the cyclone. The first step will be to read in the mesh we've just created in ICEM. So select the cyclone tutorial mesh file. And we'll go through the solution setup step by step. So in the general tab you only want to add gravity. And in this case the gravity acts in Z, or rather minus Z direction. So I'll type in minus 9.81. Then to the models tab. For this tutorial I wanted to keep things as simple as possible, so I've already chosen a cyclone for which we only need to activate a turbulence model. And in case of the cyclone we have a really complex flow field, so we need to use at least the Reynolds stress model. Any other of the Reynolds average Navier-Stokes turbulence models will give you results which aren't even close to reality. So when doing any cyclone simulations, make sure you choose at least the Reynolds stress model. And I'm going to use the standard wall functions for this one. Then in the materials tab, we don't need to change anything. Air is exactly the fluid we need. Neither do we change anything in the cell zone conditions. But we obviously have to add some information in the boundary conditions. So first let me rename this to, let's say, wall fluid. And since this is a cyclone made out of commercial steel, you can leave all the default settings. Then to the velocity inlet. Now as a specification method for turbulence I use the intensity in hydraulic diameter. And if we go back to the first screen of this tutorial, you can see in the test conditions that the incoming air has a velocity of 12.69 meters per second. And I've already prepared the hydraulic diameter for the velocity inlet as well as the hydraulic diameter for the pressure outlet. Another thing you can see in the test conditions is that the cyclone operates under really low particle-laden conditions. So the procedure will be to, first we're going to calculate the flow field in the cyclone, and after that we're going to inject some particles in the inlet using the discrete phase model, which is really the standard procedure for any cyclone simulations, but you're going to see this in a few minutes. So back to Fluent, we'll type in the velocity magnitude of 12.69 meter per second. And the hydraulic diameter of 0.127. And since we're only using a turbulence model, you don't have to worry about any other boundary conditions, and simply hit OK. Then to the pressure outlet. The only thing to change here is the specification method. So pull down to intensity in hydraulic diameter and type in the diameter of 0.15 meters and hit OK. Lastly, let's change the display of the mesh and change the edge type from all to outline. And that's really all you want to do for the solution setup. And we can proceed with the solution now. And first we're going to initialize using the hybrid initialization. And after that we can start our calculation. Let's do a number of iterations, say 5,000. That should really do the job. Click calculate. And this is going to take at least a few hours, depending on your local machine. Now first of all, don't worry about that reverse flow on pressure outlet message. That's exactly what we want in a cyclone. In fact, there would be something really wrong if there isn't a reverse flow on the outlet. But as you can see here, even after 5,000 iterations, we did not reach any convergence. The solution usually fluctuates at a certain value. Now this is mainly caused due to the fact that we chose the Reynolds stress model to simulate the flow field of the continuous phase. The Reynolds stress model might be the most sophisticated Reynolds average Navier-Stokes turbulence model, and the only one able to describe the inner solid body rotation and the outer free vortex in a cyclone correctly. But a downside to the Reynolds stress model is that it is really sensitive to the designed mesh. Now for my master thesis, I've modeled several different topologies, which most of the time were a lot more complex and detailed than this simple standard cyclone. And I hardly ever got convergence of the solution when using the Reynolds stress model. Now what I usually do is to switch here from a steady simulation to a transient one. But before changing any settings, let's save the current time step. And then we go to the General tab and switch time from steady to transient. And if we go back to the Run Calculation tab, you can see that we now have to define new solution settings. Now for the following part, I should strongly point out that I really don't know how a professional engineer would proceed at this point. Like in the meshing part before, all my settings and methods are solely based on my interpretation and 5 months of CFD experience, if you want to call it that. And I usually start with a time step of 0.01 seconds. And I leave the 20 iterations per time step. And to keep things simple, I also leave the under relaxation factors as a default here. And let's do a number of time steps, say 10, and calculate. You can see that our solution started to converge. The idea now is to decrease the time step size and at the same time increase the iterations per time step. So let's do 0.005 seconds for the next time step and 40 iterations per time step. Again, we're going to calculate 10 number of time steps. What makes the solution converge even further? Next, a time step of 0.001 with 50 iterations per time step. And let's do here only 5 number of time steps. And finally, the residuals for the continuity equation sank below a value of 1 times 10 to the power of minus 3, which Fluent reports as a converged solution. Now we could continue this method, but at that value the flow field in the cyclone is normally approximated quite well. This means we reached the final part of this tutorial and we'll determine the fractional separation efficiency and the total pressure drop. As I mentioned during the meshing part, we will use the discrete phase model to simulate spherical particles as a second phase in the cyclone. In the Models tab, activate the discrete phase. And first let's specify some tracking parameters. And make sure you uncheck unsteady particle tracking. And let's create an injection. And I usually use a surface injection type of inert particles on the inlet surface. And we could use the Rosen-Ramler diameter distribution to inject particles with different diameters. But to keep it simple, I'm going to inject only 1 micrometer particles. I assume the particles to have the same velocity than the incoming air. Since we are using a static particle treatment, the total flow rate doesn't concern us at all. You can set this up to 100 kilogram per second, won't make any difference here. Neither am I going to use any of the advanced settings in this tutorial. So we simply hit OK and OK again. In the Materials tab is now a new material type, which are our particles. And one thing to change here is the density. If we go back to our test conditions, you can see that the limestone particles in the experiment had a density of 2770 kilogram per cubic meter. So back in Fluent, we give our particles exactly that density. Last thing for the particle settings is to define some boundary conditions for them. With the discrete phase model activated, you can specify some boundary conditions, and particles should be reflected at the wall, and they can escape via the pressure outlet. The only thing to change here is the wall dustbin discrete phase model boundary condition. All the particles which separate from the carrier gas due to centrifugal forces and sink towards the dustbin should be reported as trapped. So pull down here to trap and hit OK. Okay, that's pretty much all you gotta do to set up the particle simulation, and we can start with the particle tracking. So go to Graphics and Animations, Particle Tracks. Let's choose our injection and start the tracking process. So this is going to take a few moments because we did set a quite large number of time steps. But eventually Fluent will report the results of the tracking. And let me display some of these trajectories. So skip, let's say 20, Corson 100. Also draw a mesh. And display. You can see we released 378 particles, one from each facet at the inlet surface. 320 of them escaped through the vortex finder, while 57 got trapped at the dustbin wall. And there is unfortunately a third type of particle result which is reported as incomplete. Now that's an occurrence which often appears in cyclone simulations when using the discrete phase model. This incomplete particle kind of got stuck in an infinite loop and it swirls up and down again, never reaching the outlet nor the dustbin wall. In reality, this particle would sooner or later collide with other particles, and depending on the impact angle and particle properties, it will get collected or escape. The discrete phase model, on the other hand, does not take into account any particle collision, at least not with our current settings. So this particle will swirl up and down infinitely and thus be reported as incomplete. If it's only a few particles, I normally don't worry about it and just get on. Now with this tracking report, we can determine the fractional separation efficiency, in this case for our injected 1 micrometer particles. The separation efficiency calculates as the number of trapped particles divided by the number of injected particles minus the incomplete ones. And let's compare this numerical prediction with the experimental crate efficiency curve. You can see we have a pretty close match. I've already prepared some further numerical results, and our model is seen to predict the actual performance quite well, even with the simplified assumptions. Finally, we need the second key performance indicator of the cyclone, which is the total pressure drop. So back in Fluent, we'll go to Reports, Volume Integrals, Setup, Pressure, and we need a total pressure, and integrate over the fluid cell zones. Compute. And the numerical model predicts a pressure drop of 1285 pascals. And let's compare this again to the experiment. You can see that we have a difference of about 12 pascals, which I think is still quite okay. This is a cyclone simulation after all. So we are basically done with the tutorial part. And additionally, I want to show you how to create a simple animation of our cyclone separator. For this, we are going to treat the particles in a unsteady fashion now. So check unsteady particle tracking. And since the cyclone operates under really low solid loading, I'm still leaving interaction with continuous phase unchecked, meaning we still assume a one-way coupling. If we go to the injection setup, I'm going to use the Rosen-Ramler distribution and define my diameters. And I want to release 3 diameters. Furthermore, I want to do a single injection in the following calculation. So I'm setting the start time to 0.16 as well as the stop time to 0.16. And because of that, the total flow rate is still irrelevant. So, okay. And I want to take a picture of my particle position at every time step. And this can be easily done with the calculation activities, solution animations. We need a single sequence. And I want to take a picture at every time step. I want to take a picture of my particle tracks, and we need a mesh, of course. And let's give this a marker size of 0.3 and color by particle diameter. Choose our injection and display. Okay. Back to the rank calculation tab. Now the whole separation process shouldn't take longer than maybe a second. So let's do 1000 iterations, and 10 iterations per time step should be enough. Calculate, and you can see that particles have been injected at the inlet surface, and the whole calculation process will take again a few hours. And finally, we need to save our animation after the calculation. So go to Graphics and Animations, Solution Animation Playback, Setup, and write your sequence as a MPEG format. Now let's have a look at that animation. We got our 3 different diameters here: blue 1 micrometer, green 5 micrometer, and red 10 micrometer. And if you play the animation, you can see that the red particles are instantly slung outward to the wall and are transported downward to the dustbin by the downwardly directed gas flow near the wall. And of course, the blue 1 micrometer particles are sooner or later forced into the inner region of the cyclone, where the axial movement is upwardly directed and they exit through the vortex finder. So we are at the end of my tutorial. Keep in mind that all the meshing and simulation settings are mostly based on my own interpretation. I cannot guarantee that this is like the official procedure. Of course, there are much more detailed ways of simulating a cyclone with Fluent. I strongly recommend the ANSYS Fluent user guide and theory guide for that. Thank you for watching.